Right, welcome to the second part of my lecture on string duality. So I want to think about string theory compactified, so that we're thinking about a space-time which is some d-dimensional space times some internal space, let's call it n dimension, little n. So you're thinking about having some n-dimensional compact space and the product of this with a space-time, so that, for example, we're talking about a 10-dimensional space, so that this M might be 4-dimensional Minkowski space and N might be a torus, or it might be a Calabi-Yau manifold or some other manifold. So the geometry on N. So this theory will be by the moduli of n. So these are the parameters which determine the structure here. So for example, if n was a circle, the modulus would be the radius of the circle. If it was a torus, there'd be radii for each of the circles and the angles between the circles. If it was a sphere, there would be the radius of the sphere, and so on. And there'd be a number of parameters describing the geometry, which could be thought of as relating the parameters which parameterize the metric on n. Plus there'll be other parameters which represent some of the other fields, like the B field, and their values on n. So we have a set of values, so let's call these mu1, mu2, and there'll be some finite set of these. Now, right, these are the vector. So we get a theory with couplings lambda, which consist of the coupling constant of the string theory coupling constant and these moduli mu, and which the G determining the interactions. And because the geometry of n can vary as we move over M, in fact, the moduli will really be fields on M. And so each of these give rise to scalar fields on M. And as a result, we can think of all of these moduli as being expectation values of scalar fields. G is related to the dilaton. The mu will give rise to fields down here. So for example, if n was a circle, the radius of the circle is given by the component of the metric in that direction, and that metric can vary as could be a function of the coordinates on M, and so that would be give rise to a scalar field. And the perturbative region is defined as in terms of the region where G is small. And in fact, these define a manifold, which will the moduli space, the space in which these coupling constants or these scalar fields live. And one can see that by when you look at the dimensionally reduced theory, the scalar fields are governed by an action which in which there's a natural metric, and that metric will tell you about the geometry of this manifold M. And in fact, in a lot of the cases we're going to be looking at, this manifold M is in fact a coset space, a quotient of two Lie groups. So suppose we have two theories, theory alpha and theory beta. So each of them is defined by some string theory alpha, which might be any one of the 5 superstring theories, or compactified on some manifold n alpha, and another string theory, which may be the same as the original one, or it might be a different one, compactified on some other manifold n beta, and we'll have some coupling constants lambda alpha, which are the coupling constant of the original string theory and the corresponding moduli, and another set beta, which is G beta U alpha. So a duality is a map F from theory alpha to theory beta, which in particular takes lambda alpha to lambda beta, which is F of lambda alpha. This is required to preserve the physics. So the idea is that this should give 2 different descriptions of the same physics. And for this to be the case, the first requirement is that the moduli space of alpha should be the same as the moduli space of beta, so that, or rather should be isomorphic to that, so this map gives a one-to-one correspondence. So we can think of this as giving 2 different prescriptions of the same physics, that the alpha description or the beta description describes the same physics. So this is a familiar concept. We know that if we think about two apparently different manifolds, n alpha and n beta, if they're in fact the same manifold related by a change of coordinates, the same manifold in different coordinate systems, then the theory on n alpha and the theory on n beta are related by a diffeomorphism. And the physics is the same, but there's a map which tells you how you translate things in one theory in one coordinate system to the one in the other theory in the other coordinate system. So here it's a sign that there's a symmetry which is telling us that the theory is the same. So we're going to look at lots of examples of this, but I just wanted to get the general idea. So we have, if we were to draw the moduli space of m alpha, parameterized by the lambda alpha, and the moduli space of m beta, parameterized by the lambda beta, there's a region here in which it's weakly coupled is defined as a perturbation theory in one of the parameters, lambda, the G. And this, in general, will map under F to a region here, which might not be weakly coupled, whereas there might be a region here which we're interested in where this is strongly coupled, for example, where G is large, and this will be mapped to some other region here, and we'll be interested in the case where this is in fact a region where this is a perturbative theory in the coupling constant G beta. So that we have this picture where the duality will relate two apparently different theories, and it may relate perturbative theory in one to a non-perturbative theory in another. And we can consider a number of different cases. First of all, we can consider non-perturbative duality, where G alpha, the coupling constants are the same, or possibly they could be proportional to each other, or some relation where when one is small, the other is small. But the mu alphas are non-trivial functions of the mu betas. Sorry, I had it the other way. The mu betas are non-trivial functions of the mu alphas. And so the map will change the moduli of one to the moduli of the other. Will be a non-trivial map on the moduli, but the coupling constants will be the same. And this will be the same. And so we'll get a theory where we can analyze things within string perturbation theory. And examples of this are T-duality and mirror symmetry. And we'll talk about these about T-duality in a moment. But the key point is, because we're relating a perturbative theory to a perturbative theory, we can check this entirely within string perturbation theory, and we can prove this within string perturbation theory. And so this is an area where we can establish we can establish with some degree of rigor that there is such a duality. Another case is where we have a strong weak duality, sometimes referred to as an S-duality, where G beta is 1 over G alpha. So in this case, when G alpha is weakly coupled, when G is weakly coupled, G beta is strongly coupled, and vice versa. So the strongly coupled behavior of the original theory alpha can then be understood in terms of a perturbation theory for the dual theory beta, and vice versa. An interesting case is when we have self-duality, in which theory alpha is equal to theory beta. And so this, then F is a map on the moduli, and it gives so F from lambda alpha to lambda beta, and in this case this will then provide a symmetry of the theory alpha, and the set of all such F preserving T alpha forms a group which is the a symmetry of the string theory. And it's the emergence of this enlarged symmetry which is rather striking, and it's telling us that string theory is a theory which has extra symmetries beyond any which are seen in field theory, and these symmetries are going to play a key role in this lecture. And finally, there will be dualities which are none of the above, which will just be non-perturbative maps which don't preserve, which will mix up, in general, could mix up the coupling constants with the moduli, and will give rise to a more general set of transformations. So the question then is, how does one show that these really are symmetries, that there really are, that there really are these maps, these duality maps, and the two theories are define the same physics? And part of the trouble in defining that is we don't know how to define, in showing that, is we don't know how to even begin to talk about what the physics is for string theory at strong coupling. But it turns out that in the supersymmetric theory, supersymmetric theories, there are certain properties which are protected by supersymmetry, which we can extrapolate from weak coupling to strong coupling. And these will provide the key to unlocking the structure of the non-perturbative dualities. So the perturbative dualities we can, to some extent, prove within string theory, but the non-perturbative dualities are ones where, because the theories are not completely defined, we formulate a conjecture that there's a relationship between two theories, and then we investigate various bits of evidence, and we try and amass evidence, and in particular, we look at detailed tests to check whether it is the conjecture could be true. And so one finds, as years have gone on, we've assimilated an overwhelming amount of evidence in support of these non-perturbative dualities. But it's important to remember that they're not proved, but in some ways they can be thought of as defining a definition of what it is, of what the strongly coupled theory might be. It's defined as the perturbation theory of the dual theory. So I'll stop part 2 here, and I'll continue the lecture in part 3. Thank you.